we'll talk about L'Hopital's rule. This is a technique that allows for evaluating limits of expressions where we encounter a problem because we cannot evaluate at the point because we have something that's not defined. So where things are not clear. So when you have competing effects, like two things going to zero at the same time, going to infinity at the same time, or you have something very small multiplying something very big, and when it's not clear which one is going faster to, say, infinity or zero, you don't know what the limit will be. So the most basic form of the problems that we can tackle using this technique. So the most basic example, and in fact we're going to cover this first because all the other applications are gonna be obtained from this application. So we're going to reduce all the other expressions to an expression of this form. So something divided by something. So two functions that are approaching zero at the same time or infinity at the same time, and one is when you're dividing one by the other. So basic example is to evaluate. You want to evaluate the limit of a quotient, say f of x, divided by g of x, as x approaches some constant a. Just like in the beginning of the course, f need not be defined in a, neither does g. And in the most basic application, we're in a situation where f of x and g of x both go to zero at the same time when x goes to a. So of course that is problematic because we cannot just compute 0 over 0. That's not defined. And another situation that needs special considerations to handle it is when both f and g go to plus or minus infinity. It doesn't matter. I mean, f could go to plus infinity, g could go to minus infinity, but any combination of infinity divided by infinity or plus infinity divided by minus infinity is not clear whether this is going to 1, going to 0. Depending on which one is going faster to infinity, it may be 0, maybe infinity, minus infinity, plus infinity. So this is the basic example. This is the first application that we'll see, and we'll state the rule for this kind of situations, and then we'll apply it to some other expressions as well. So what is the rule? What does the rule say? So what are the conditions for the result? So if you have that f and g are differentiable, on an open interval containing a and f of a equals g of a, and they're both equal to 0. And furthermore, g prime of x is not equal to 0 for x not equal to a. Inside this interval. Then, to compute the limit, we can transform the problem of computing the limit as x approaches a of f of x divided by g of x to the problem of computing the limit as x approaches a of f prime of x divided by g prime of x. Okay, so we can, so in order to, this is a warning here, this is not the quotient rule. People, when I give a problem to people and ask them to compute the derivative or apply the L'Hopital's rule, they somehow get confused from time to time and apply the incorrect rule. So here, what this is telling us is in order to compute this limit of this quotient, we can differentiate the numerator and the denominator and apply and try to compute the limit of this expression on the right. So what we don't know is how usually we go from the left-hand side, which we don't know how to compute or evaluate, and we differentiate the numerator and the denominator, and that will hopefully lead us something that is more manageable. The rule also applies, which is another case, the other case that I was mentioning before, also applies when f of x and g of x go to plus or minus infinity at the same time. Okay, so the hypothesis, if f is going to 0 and g is going to 0, you can apply this rule provided the g prime is not banished in an interval containing a. You can say the same thing when f and g are both going to infinity. And in that case, you can also differentiate f, differentiate g, and compute the quotient and take the limit of that expression instead. But so the hypotheses are very, very important. Okay, very important. So we're gonna see a few applications in the next video, but for now I can tell you for sure that there are situations in which you cannot apply L'Hopital's rule. So first, few examples. Something that you're already familiar with is when you want to compute, say, the limit of 1 minus e of x divided by sine x. X approaches 0. And how do I know that you already know how to handle this situation? Because you already know the limit of 1 minus e to the x divided by x as x approaches 0, and you also know the limit of sine x over x as x approaches 0. So you could multiply and divide by x. But here we're just interested in finding out whether we can apply L'Hopital's rule or not. So can we apply L'Hopital's rule? Okay, let's see. F of x, in this example, is 1 minus e to the x, and g of x is sine of x. What is a? A here is the point 0. Okay, so what do we need to check? So what does f go to? F of x goes to what as a goes to as x goes to 0? Well, this is the same as 1 minus e to the x, and e to the 0 is 1, so this goes to 1 minus 1, which is 0. Okay, so f of x goes to 0. G of x, which is sine of x, also goes to 0. Sine of 0 is 0. So the first part is done. Both f of x and g of x tend to 0 as x approaches the point a, which in this case is 0. Okay. So first condition is checks out. The second one is also true. So g prime of x, which is cosine of x, is not equal to 0 near x equals 0. Because, well, cosine of 0 is 1. Okay? And so all nearby points, cosine is going to be very close to 1, so it's going to be different from 0. So we can apply L'Hopital's rule, and we can compute this limit. Instead of computing this limit, this tells us so L'Hopital's rule applies. So we can apply L'Hopital's rule and obtain the limit as x approaches 0 of 1 minus e to the x over sine of x is equal to the limit of f prime. But what is f? 1 minus x. So that's the derivative of 1 minus e to the x divided by sine of x. And the derivative of 1 minus e to the x is minus e to the x. And the derivative of sine is cosine of x. So now we have an expression where both functions are continuous and the denominator doesn't vanish at the point. So if you remember from our first couple sections, the first couple of weeks, we went over one of the limit laws that told us if the functions were continuous and if the denominator in a rational expression or a quotient was not equal to 0, then we can just plug in the value. So this would be equal to minus e to the 0 divided by cosine of 0, which is then equal to minus 1 divided by 1. So in the end, this whole thing is equal to minus 1. Okay. Well, now, then this was part of the point I was trying to make here at the beginning when I said that the hypotheses are very important. We checked out the hypothesis in order to apply the rule in this example. Okay, so what about another situation like this one? So suppose that instead we were asked to compute the limit, find the limit when x approaches 0 of 3x divided by, say, 4. This is a kind of a silly example, but so here we're not in a L'Hopital's rule situation. Here f of x is equal to 3 of x. G of x is a constant function 4, and the point is, again, the point A is 0, yet while f of x goes to 0 when x approaches 0, g of x remains constant and so approaches 4 as x approaches 0. So you can only apply L'Hopital's rule if both things, both the denominator and numerator, tend to 0 at the same time as you approach a point, or they both approach plus or minus infinity. This is not one of those situations. The numerator is approaching 0 and the denominator is approaching 4. Why did I use this example? Because we already know what to do here. When you're computing a limit, this expression here is just 3/4 of x. That's a continuous function. So we just need to evaluate the point. So that will give us 3 over 4. 3 over 4 times 0, which is 0. But what if we try to apply L'Hopital's rule, which would be incorrect? So if we had tried to we would get the limit as x approaches 0 of the derivative of the top, which will be 3, divided by the derivative of the bottom, which is 0. And that's not even defined. This is not plus infinity, just in case. Because this is effectively equal to 0, the derivative of the denominator. Okay, so the rule doesn't apply here. So it's very important to check. We already know the limit is equal to 0. We can compute it directly. So, and the good news is that here you already know how to compute the limit. So you only need to apply L'Hopital's rule when you don't get anything. I mean, when it's the expression you get is undefined, or you have an indeterminate form. Here it's not indeterminate, so you can just use some of the rules you already know. So, and when that fails, then you're probably in a situation where you can apply L'Hopital's rule. So you need to check the hypothesis. That's the point I was trying to make here. Check that both numerator and denominators tend to 0 at the same time. If not, you need to apply something else. Or, no, the other situation, as I told you before, was when both numerator and denominator were diverging or going to infinity, plus or minus infinity at the same time. See you in the next video.